All right. This, okay. So remember how we did multiplication and division? That was 6.2. Um, this is a different kind of multiplication division. It wasn't sort of looking inside the radical. So in I think it was 6.2, we looked at inside the radical. So we can multiply radicals. This time we're going to look at what happens with multiplication between different types of radicals and division between the different types of radicals. So let's go for it here. Nothing sort of new. We'll look at examples as we go. All right, and if you remember last time, remember outside numbers have to multiply with outside numbers. So the 7 to 5 has to multiply, and that will give us a 35. Then what we do is we look at the inside numbers. We're going to multiply those. So 3 times 11, 33. The only thing we still have to check is if 33 is a perfect square or has a factor of a perfect square. I don't think so. 3 and 11 make 33. That's it. Cool. So we're done. There's your multiplication. Of course, it gets more complicated though. So this is a single term times another single term. That's what we got here. Let's go down here. Let's go with the one term times two terms. And again, you've got to think about it as just distributing. That's all. The root 2 goes to each one of those. And a little quick shortcut here in just a little bit here. All right, if I do that, and then the root 2 has to go to the other one. So again, 3 is the outside term. It's going to stay as a 3. But root 2 times root 5, got ourselves a root 10. So multiply the inside terms. Minus sign is fine. Again, the 4 is on the outside, so 4 stays as 4. All right, let's do this the quick way. This would be square root of 2 times square root of 2, which is going to give you square root of 4. And square root of 4 is not already a perfect square. So in this case, we'll just write it as multiplying a 2. Because remember when we do, quick aside here, the whole distribution here, remember how we do this? Now, right? The 2 goes to the x. That gives you that, but it doesn't affect this one because this has to still go to here to give you a 2 times 3. So same exact concept. Okay. It does. It becomes this. And then this rule is from 6.2. It says if I'm multiplying two radicals together, I can multiply them inside a single radical. Good there? That comes from 6.2. Okay, are we okay with the 2 times 4 though? Okay, so that stays as 3 root 10. There's no perfect square in 10. And this becomes an 8. And your book, and again, other math textbooks, it doesn't matter which way you write it usually. So you can put the little negative 8 in front and put the 3 radical 10 in the back. Both those are correct answers. Let's see, if you talk about a little bit slightly above majority, math textbooks would probably write it like this. They will like to write the number that does not have the radical first, and then they write the ones with radicals. And the funny thing is, then they'll write it as increasing numbers inside the radical. So they write like this. If it was a 3 root 5 inside here, they write that first, and then you have a 3 root 10, then 3 root 15. They do that. So the radicals start increasing in the number. Your book, it doesn't care which way to write it. I don't care either.
Could you do the stuff in parentheses first, or do you have to times that round to it?
Good. Question is, can we simplify this? You can't simplify this because the two radicals are different.
Could you times them together and deal with all that first?
Yeah, if this was a radical 2 here,
Okay.
then yes, you could have. Then it would be a negative radical 2 times radical 2, which would be a negative 2 at the end. Yeah, so yeah, you can, but at this point, this guy can't be put together. Good questions coming up. I tell you guys are awake today. Oh, that's right, because it's cold in here. That's why everybody's awake. Everybody can't fall asleep. Okay, Ooh, two terms times two terms. Looks like FOIL to me, doesn't it? Each term in one parenthesis has to multiply the term in the other. So first one, outer ones, inner ones, and last ones. That's what we have to do. All right, let you guys try that one here. All right, I'm going to start it as well here. Let's see what we got here. So root 2 times root 2, hopefully just wrote down 2, right? Because it'll just be a square root of 4. All right, this one here, multiplying the outer ones, so minus 3x, minus 3, sorry, minus 3, and this would be square root of 14. Good there. Because 2 times 7, they're both inside numbers. All right, the inside stuff right here, square root of 7 times square root of 2 would make plus radical 14. And then at the end here, so again, technically you think of this as like a little 1 right here, so 1 times negative 3 is a negative 3. And radical 7 times another radical 7 makes radical 49, which really just makes 7. And again, if you could put down a 21 already here, that's fine too. But simplifying out, let's see, I got x, sorry, 2 minus that, and I got myself a minus 21 over here. It's kind of simplifying the 3 times 7. Okay, then do we have like terms? Yes, we do, right? The first term, 2, and the last term, negative 21, those are like terms. So add those guys up to give me a negative 19. And then how about a negative 3 root 14 plus another root 14? They are the same because they're like radicals, right? They both have radical 14 in them. So I can combine those together. So we combine it with a, what's a negative 3 plus 1? Negative 2 with the radical behind it. Go there. All right, see a lot of eraser marks here, so talk to me. What happened there? We should have done that together. Okay, everybody good there? Any other questions, like where did the 2 come from? Where did the... Okay, let's go for it now. Let's introduce the variable. So now we have x is the variable. All right, this little 2 here, I think you guys know what that means, that there's 2 of these. All right, remember with polynomials, this was a special form. With radicals, it is not a special form, so you just do FOIL. There are special forms we'll get to in a little while. This one's not. So, FOIL as usual. Let's go for it here. So square root of x times the square root of x. Square root of x times 5. Again, inside numbers would be this one and this one. I can give you guys maybe 30-second head start here. right, let me start. Let's do the question.
So the only thing on the previous one, I just didn't know, like if add the portion together, that's why.
Got it. Okay. Yeah, you can't add the stuff inside the radical, but you can add the coefficients of those radicals.
Yeah.
Almost like 3x plus 1x makes 4x.
Yeah. So that was the only thing I didn't know, so I kind of understand how it works.
Mm-hmm. Cool. Okay. You're good. All right, let's go for it. So square root of x times square root of x would just be x. Hopefully we did that. Right, because it'll be producing a square root of x squared. Also, the directions on the homework, it actually says assume all your variables are positive, right? Because we don't have to do the absolute value or not absolute value of that stuff. We don't have to do that. Okay, so outside terms, 5 and then a root x would make a plus 5 root x. Inside terms, 5 times root x is 5 root x. And the last terms, 5 times 5 should be 25. Okay, like terms, yes, those guys. So we got x plus 10 square root of x plus 25. Kind of doesn't look like a sort of trinomial though. Instead of x to the second, x to the first, and no x at all, it's actually x to the first, x to the 1/2, and no x. So it's kind of funny how it still goes down. With polynomials, it went down by 1. Here it actually goes down by 1/2.
The way it, because it looks
We
like
just
it's
might.
back. The way it looks right there, it
Uh-huh.
looks like something is supposed to be back there.
Uh-huh. Sorry.
It doesn't look
That's why it says expand on the directions. Okay. A little bit more difficult. I think you guys can handle it. We'll try it yourself here. So 5 and 6, give you guys maybe like up to a minute. Try it, and if you're sort of not quite sure, just wait. But give you guys a minute. All right. Let me see if you're still working on it here. Wait a little bit. All right. Let me start. So that means that there's two of the same exact kind. And again, multiplying in. That's 5 times 5 is 25, but then the a is going to be perfect square, so it's just 25a. Outside terms, 5 and -3 make -15. A and the b are different. They're not the same, so it'd just be a square root of ab. Both of them underneath the radical. And then in the middle, I got -3 and 5 make -15. Again, a and the b are different, so it'd be just ab. What I should do as well, I should make sure I extend this out beyond the b just a little bit to make sure that everybody knows the b is inside that radical. Same thing over here, just extend it just a little further here. Okay, and then -3 times -3 is a +9. And then square root of b, which becomes just a regular b. Like terms, or like radicals, yes. The middle terms again. So that means 25a minus 30 square root of AB plus 9B. Real quick here, show of hands. Somebody got that one correct before I did. 6. Yeah. And everybody on this side. Nobody on that side. Okay, this one again, the same exact thing here. We're going to multiply those guys. Now we have a binomial inside the radical. That's okay, still same process. So multiplying the first ones gives us x plus 3, because that's exactly what's inside, and we just form that perfect square. Outside terms, it's that times a negative 1. So all the thing it's going to do is going to change the sign. So it's negative of x plus 3. All right, and then the other way, negative 1 times that, again, is just going to change the sign of x plus 3. And the last one is going to be just a positive 1. At that point, like terms. Yep, x does not have a like term. We'll write that down. But you do have the 3 and the 1. Those are like terms. It changes into a 4. And then these guys are like radicals. So negative of this and another negative of that makes 2 negatives of that. Alright, so as I said, there are special forms. This one is a special form. In fact, has a little special name for it. These guys are called conjugates. We'll need them later. Not the word, but as long as you recognize the form. So what's so special about them is the exact same radicals inside here, exact same numbers, except sign in the middle has changed. Polynomials, remember we called them difference of two squares. Remember that? And what does the difference of two squares do? They cancel off the middle terms. So what's so special about this here is whenever you multiply conjugates, you have perfect squares at the ends. So square root of 5, square root of 5 is just 5. And as you multiply the outside terms, that gives you radical 15. But because they have different signs, it would give its opposite as the next term, right? And at the end, again, since you have perfect squares, middle terms cancel. So what's so special about conjugates is if you multiply by a conjugate, there are no more radicals left. You have a way to get rid of radicals. So 5 minus 3 is a 2. Notice no square roots here, no nothing. Which is kind of cool. So if I need to get rid of radicals, I multiply by the conjugate. When do I need this? I need this for the next problem. Look at that. What a good setup. Okay, this whole concept of rationalizing the denominator. In mathematics, most of the time, not all the time, most of the time, we don't like to see radicals in our denominator. That would not be considered simplified. There's very few exceptions. When you're graphing stuff, you may want to see that because it looks a little better. So, I got this little problem. Question is, what should I multiply by to get rid of the radicals in my denominator? Perfect, yep. It's the exact same numbers with a plus sign instead of a minus sign. Whatever I do to the bottom, I better do to the exact same thing to the top. Now, real quick here, since the middles are going to cancel, do I even need to multiply the middles? No, why do extra work when we don't have to, right? The only thing I really need to multiply is the first numbers, which is a 7, right? The middles are going to cancel, so no multiplying there, and the last numbers. That's it. Good there? Because why? Because it's going to be a positive square root of 21 and a negative square root of 21. At that point, they're going to cancel off anyways. All right. Only thing, warning I give you guys for the homework here is see this little 3 on top? sometimes this 3 will actually reduce with this number here. Let's like what happens if it was an 8 or something, right? That 8 and that 4 would reduce. So before you multiply things across, if this reduces, bring it over here and then just reduce it first before you multiply. If it doesn't, then yes, then just multiply 3 times square root of 7. 3 times radical 3, which makes 3 root 3. Okay, so this would be considered simplified. So I have no perfect squares inside my radicals, and I have no radicals in my denominator. And I have nothing this 4 can factor down into. Okay, number 9 is a little bit more tough. But again, let you guys handle that one. So first is what should we multiply by to rationalize the denominator? Yeah, we're going to multiply what's on the top. It's going to be square root of 10 minus 3, right? Not because it's the numerator, but because it's the conjugate of the denominator. And why does the book show this? Because sometimes that's what happens. You'll have conjugates, ratios of each other in mathematics. Question again? Sometimes the conjugate's unknown. Like on the previous problem, it wasn't. There was just a 3. But as long as you see radicals here on the bottom, you got to multiply the conjugate almost all the time. All right, let you guys finish that one off. Give you guys a minute here. Just try yourself, see if you can finish it off. All right, I'm going to start here as well. So for the denominator, let's go with this. So again, multiply first term, square root of 10 times square root of 10 is just a 10. 3 and negative 3, remember these are not inside the radical. So this is actually a full 3 times a negative 3, which makes 9 this time, right? So 10 minus 9 is a 1. On top, yes, we got to do all the FOIL. So this one, got to multiply those guys, gets us 10. Outside terms gets us a negative 3 root 10. And you know what, I got to extend this quotient bar way over here. So let me extend it further. First outside, now inside. So negative 3 times root 10 makes a negative 3 root 10. And last, negative 3 times negative 3. Positive 9. Okay, since the 1 is in my denominator, there's no denominator whatsoever now, or the numbers cancel. So putting it together here, 10 and 9 make 19. And let's see, yeah, both have radical 10, so it would be negative 6 radical 10. And the next one has to do with this golden rectangle, which kind of shows up at different times. We're just going to skip it for now. It's just an application. It's not that cool of an application. If it was a cool application, we'd do it. But... Okay, so 6.5 is the longer section of these two. So let's take a look at these. And so far we've been doing is we've been simplifying, right? We learn how to multiply, divide, add, subtract. Now we finally get to more like an algebra aspect to it. This is now solving equations. That's what algebra is, solve equations. So we got one little problem though. Let's talk about it. This one you have to get because this is a concept. So the way we get rid of radicals in our equations is if we need to, we can square terms. If we need to, we can cube terms. So notice if a is equal to b, all I'm going to do, I'm going to square both sides. That's good enough by me. So a good example here, 7 is equal to 7, we good? If two things are equal to each other, if I were to square it, does that for sure mean that they're going to equal to each other? Yeah, because I'm doing the exact same thing to both sides of the equation, right? Square 7 on that side, it gives me 49. Square 7 on that side, obviously it's always going to give me the same thing. Cool. That's not the problem. The problem comes in on this side. Let's try negative as well before we do that. Let's do this here. Will a negative work the same way? If I have two things equal to each other and I square them, can I still keep my equal sign? Yeah, the negative goes away, but I'm not really interested in that. I'm interested in make sure I can keep my equal sign. So yes, that's perfect. That's what this is talking about right here. All right. The problem comes in is this over here, in the middle. Is 5 equal to negative 5? I don't think so. We should put a little slash like this through that. That's not equal to. But the problem is when I square it, they do become equal. So it could be that something was not equal, but when I squared it, it turned out to be equal. All right. We got a little word in here. It's called extraneous solutions. Kind of fun little word here. So whenever I square two sides of an equation, there is the possibility that I had that situation happen. That means I have extra answers that are really not answers at all. So how do we combat the situation? Ready, ready? We always check our answers. Always, always, always have to check our answers. All right, so let's do a little bit more here. So we know this is a possibility, right? So negative 2 not equal to positive 2. I square both sides. Now I got myself something equal to. There's your extraneous solution. Pretty good? And notice what's really happening is because of that negative. We'll talk about it later. But let's go on the other side here. Next question. What happens if it's taken to the third power? Is that okay? So first of all, let's check this right here. Is this true? 2 is equal to 2? Again, put your thinking caps on for a little bit here. This is going to be 8 is equal to 8. Is that good? If I take things to the third power, I can keep my equal signs if they're equal to already. But my question is, what happens if they're not equal to? What happens if this is a negative 5, this is a positive 5? If I take it to a odd power, do I get this extraneous solution situation? I don't. That's cool, because 3 negatives multiplied to still keep a negative. So that's cool, and I still keep my non-equal to symbol. Good there? So really, the only problem is when you are using an even power. Right? because even powers are what's going to get rid of that negative. So careful there. If you're squaring something, taking something to the fourth, you got to check your answer. Taking something to the third power, no need to check your answer. All right. All right, with that, let's get started. In order to get rid of that radical, first of all, the radical needs to be on one side and it has to be all by itself. If it's not all by itself, you can't do this little process here. But yes, we have the radical. It's all by itself and it's on the left-hand side. So let's square both sides. And of course, the alarm goes off in your head. Ding, ding, ding. Check your answer when you're done. All right, so also notice whenever you take a square root of something and whenever you square something, those two are inverse operations, right? So what's going to happen is those two are just going to cancel. And we're left with 2x plus 4. That's why it works. On the other side, though, I should get a 16. All right, let's see. So how about subtract 4 from both sides? Gives us 2x equals to 12. Divide both sides by 2. And how about 6? All right, always got to check this one. So we're going to check it by plugging it back in. So 2 times 6 in parentheses plus 4. The question is, will that give us 4 on the other side? Let's see, 2 times 6 is 12. And 12 plus 4 is 16. And square root of 16 is, hey, 4. Cool. All right, it did check out. It's kind of funny too, because notice the operations that we did to solve for x. We divided by 2 and we subtracted 4. Notice over here what we're doing is we're multiplying by 2 and we're adding 4. The reverse of what we did. Alright, so if that checked out, then of course x is equal to 6 is the answer and we're good to go. Okay, number 2. Let's try this one. So, look at this here. I got the radical. Is the radical all by itself on one side? Absolutely. We're good to go then. Let's square both sides. Alright, squaring both sides should leave us with a 7x minus 3 and a 25 on the other side. Good there? Add 3 to both sides gives me 28. Divided by 7 gets me a 4. And again, don't forget to check. Alright, let's check here. So 7 times 4 minus 3 equal to negative 5. So 7 times 4 is 28 again. Hey, look at that. Same exact numbers we got. Subtract 3 gives us a 25 on that side. And is 25 equal to negative 5? I don't think so. Put a slash through it. Should have put a slash through the equal sign too here. Okay, good there? If we did have another answer to check, let's say this was x is equal to 4, and then also we had a possibility of x equals 5, then we also have to check 5. And if 5 turned out to be good, then we only have x equals 5 as the answer. Careful there. All right, the question really comes up, Mr. H, how come it doesn't work? Let's talk about that for a little bit. It doesn't work because of this. Remember when we defined this little symbol right here? Remember we defined it as the positive answer that gives us the square of 7x minus 3. Remember that? But notice the original problem. Look what is happening. It's the square root, or the radical symbol, is equal to a negative 5. That's the problem. Because the square root, this little symbol, can't give you a negative answer. Because by definition it says it's the positive answer that gives us that answer. Cool. So it's the negative that's the problem. Okay, with that, let's go on to this. What happens if the radical is not all by itself? Well, we're going to make it to be by itself on one side. So what should we do? Yep, subtract the 2 from both sides first before we do anything else. And I'll let you guys finish that off. Alright, hopefully squared both sides gives us a 4x plus 5 equals 25. And now let's subtract 5 gives us 20. Divided by 4 gives us 5. And yes, we do have to check. And you always want to go back to the original problem. And that's kind of what you're solving for. Making sure that's actually what you're... I mean, technically you can solve the one before you ever squared it. So plug into that. Ever term before you square it. Alright, 5 times 4 is 20. And going backwards, plus 5 more makes 25. Square root of 25 is 5. Plus 2 makes 7. Perfect, it works out. Got about 3 more people still writing it down. So wait a little bit. Cool. Alright, let's go for it. Next one. Ooh, now the trouble begins. Notice you got a t that's inside the radical on one side. Then you got a t all by itself on the outside. Again, the whole process is still the same though. So do you have a radical all by itself on one side? Yep, so let's multiply both sides. Or let's square both sides. All right, and you can FOIL this out if you need to. T minus 6 times another t minus 6. Or do you guys remember the fast way to do it? By polynomials here, you take the t, you square that one. And remember how in the middle is going to double, right? So it's 2 times t times a negative 6. negative 12t. And then what we do is at the end we take the 6 and we square that one. So 6 times 6, or you can never even think about it as a negative 6 times negative 6 is positive 36. That was it's called a perfect square trinomial. That helps out pretty good. On the right hand side, those root 2, sorry, squaring something and taking the root of something just cancels. So we're left with this. All right, at this point, once you see a variable that's being squared, also the variable itself, you know you set equal to 0 and you factor, right? So I see a t squared. I also said t somewhere. Doesn't really matter where, but I see a t there, so I'm going to bring everything over to set up a 0. Let's see, looks like I'm going to add 4 as well. Add 4 here, add 4 there, and voila. Negative 13t plus 40. I've set it equal to 0, and we're going to factor this down to see what our possible potential answers are. So I need two numbers multiplied to 40, add to negative 13. Negative 8, negative 5 would work, yep. So t to make t squared, minus 5 minus 8. All right, and the easy way here. My potential answers are, there they are. We got to check. And if I say, let's see, maybe maybe 60% of the time, one of them is going to be the answer only. About 30% of the time, none of them will be the answer. And then 30% of the time, both of them would be the answer. Cool. So yeah, you have a choice of 0, 1, or 2. So still, you got to check each case. 40, 30, and 30. A little better there? Yeah. Let's get my math right. Okay. Okay, hopefully you guys checked it. X equals, t is equal to 5, plugged it in. So 5 minus 6 is equal to the square root of 5 minus 4. Alright, and give you a little bit of the shortcut here. Notice 5 minus 6 is a negative 1. And so the question is there ever a time that a square root can equal a negative number? I don't think so. And again, it's the signs that are the issues. That's going to be not equal to. Okay, that doesn't mean that there's no answer, because we just checked the 5. We also have to check the 8. Alright, plugging in the 8 this time. 8 minus 4 on that side, 8 minus 6 on the other. So I got a 2 here. I got 8 minus 4 is the square root of 4. And yes, that does check out. Perfect. So only one answer here. T equals 8. Cool, cool. Alright, next one. Whew. Okay, the next level. There are two radicals at the same time. How do we get rid of that? How do we solve for that? Alright, this one's going to be a long one here, but once you get to this part, you'll be okay. So first question is, do you have at least one radical by itself on one side? Absolutely. Let's square both sides. Okay, I think that's why in the last section we actually took a square root of x minus 5. Remember that? This is square root of x minus 3, but similar. So on the other side, on the left side, square root of x minus 9 goes away. We got x minus 9. On this side, again, if you need to do it off to the side, go for it. That's what I would probably do. Off to the side of the page here, square root of x times square root of x is just x. Multiply across there, that would be a negative 3 square root of x. Inside terms, negative 3 times square root of x is negative 3 square root of x. And the last terms gives us 9. I think we did something like that previous section. Okay, let's put it together. So we're going to write, let's see, this x over here. That's good. Hey, don't I have like terms right here? So that'll be a minus 6 root x, and then we got this little plus 9. Okay, so notice, because this little radical was all by itself on one side, that radical symbol went away. Because this radical symbol wasn't by itself on one side, it still stays. That's okay though. Notice we start off with 2 radical symbols, now we're just down to 1 radical symbol. So here's what we got to do again. Isolate it again. You got to get the square root all by itself on one side. Now kind of careful, let's do this together. So I'm going to subtract x, we good there? Subtracting x from both sides to get rid of x's. I'm going to subtract 9 from both sides to get rid of the 9 here. So that goes away. The x's go away. Negative 18. Okay, so you got a choice here. You can do this one's going to work one way, number 6 is going to work the other way. The only time I would divide by negative 6 is only if negative 6 goes into 18. This was like a 19 over here, I would not divide by negative 6. We're good? Because then I have to square fractions, and I don't want to deal with fractions. So in this case, should I divide? Yeah. Now I've isolated the radical by itself. That's cool. What should I do next? Yeah, I got it. Squaring both sides again, just like we did when we started the whole thing in the first place. So I got 9 on one side, I got x on the other, and again, this is a potential answer. So our job is to check it. Plugging back into the original problem itself, we're checking x equals 9, so 9 subtract 9 is equal to the square root of 9 subtract 3. Is that true? Yeah, 9 subtract 9 is 0. So we got the square root of 0 on this side, and it says, let's see, square root of 9 is a 3. And square root of 0 is 0, 3 subtract 3 is still a 0, so it checks out. There it is. X equals 9 does work. Number 6. Again, very similar to this one. Let's do this here. Let you guys try this by yourself. See how far you can get until you get stuck. That's probably the best way to do it. And look at number 5 as you do the problem. started as well here. Just kind of look up to see where we're at now. So first of all, hopefully you guys squared both sides. Is that right? So x plus 4, that was pretty easy here. On this side, I have to do it off to the side. And let's see if we FOIL this out correctly here. So 2 times 2 is 4. 2 times all that, because it's a negative, is a negative 2 root 3x. Inside terms again. Again, same exact thing, so negative 2 root 3x. And then at the end here, so negative times a negative is a positive. And then root 3x times another root 3x will just give you 3x. It formed that perfect square and got out of that square root. Okay, if that's the case, then let's bring it over here. So 4 goes down. 3x brings over here, and then let's combine these guys. So minus a 4 radical 3x. If you got to that point, you did pretty good. Okay, now let's start moving things around. So subtract 4 from both sides. Also subtract 3x from both sides, right? Because you can cancel this and this. And if we do that, those all cancel. 4's even canceled, but we're left with a negative 2x on that side. And real quick here, show of hands, how many got to that step? At least got to that step. Cool, okay. Okay, so now the question is, if I were to divide through by negative 4, would I get a fraction? Yes, I don't want to do that. So I'm going to stop here. I would consider this as isolated. So let's square both sides. So negative 2x times another negative 2x. 4x squared is good. Going over here. If you can do this in your head, that's perfect. Because remember, this is two things multiplying each other, right? So this little 2 has to go down to the negative 4. And it also has to go down to the root 3x. So if you did that, you get 16. If you want to sort of see how it's supposed to work, this is kind of how it's supposed to work right here. All right. The 2 goes to the negative 4. The 2 also goes to the root 3x. So there's my 16. And then again, because I did that, I have a multiplier now. Whew, okay, got rid of both radicals. Now I just need to finish it off. Let's see, multiplying the 6 and the 18 makes 48. And again, once you see an x squared, you also see an x. Move things over. Set equal to 0. And you are going to have to factor. So what can we factor out of this? 4x factors, leftovers will be x minus 12. And right, so that I get 0 product property says I can set this guy equal to 0 and this guy equal to 0. Possible answers are 0 and 12. Let's check each of those. Cold. Agreed. All right, checking the 0 here, plugging it in. 0 plus 4 is a 4. 3 times 0 is 0. And square root of 4 is a 2. And 2 subtract a square root of 0 is still 2. That checks out. Sweet. Looking at the 12 here. Okay, that's 36 on that side. But let's see, 12 plus 4 is 16. 2 here, minus 3 times 12 is 36. Okay, square root of 16 is a 4. Square 36 is a 6, and then doing a little extra step here just to, I don't think so. So I got 0 as the answer. Okay, so what happens if you have two terms with radicals and they are both binomials? Again, just sort of the extra step here. All right, let's go for it. So again, the question is, do you have a radical all by itself on one side?
Yes.
Absolutely. Let's square them. Oh, that's funny. And in the previous section, we actually did square square root of x plus 3 minus 1 in the previous section. All right, so on the left, x plus 2. On the right, have to do it off to the side. So multiplying those guys together gives us x plus 3. The outside ones, again, this is just a negative over here, so that means it's going to be a negative of that value. Multiplying by negative here will give you a negative of that value. And let's turn negative 1 times negative 1 into positive 1. All right, combining everything together, it looks like an x, looks like a 3 and 1 can be combined together. It looks like a 4 there, right? 4. And negative these guys, another negative these guys makes negative 2 of these guys. Alright, again, if you can go ahead of me, go for it at this point. Just a little time, see if you can just solve it yourself before I. Alright, hopefully you subtracted x from both sides there. Hopefully you subtracted 4 from both sides and got you a negative 2 on that side. And because of that, and because you have the negative 2 on the other side, they are divisible. So divide both sides by a negative 2. 1 square root of x plus 3. Hey, now I got radical by itself. Awesome. Again, whole process starts all over again. Let's square both sides. Subtract 3. Bless you. And we're checking x equals negative 2. Let's see if that makes sense. Alright, checking x in there too. Alright, did it check out or no? So negative 2 plus 2 is a 0. So we've got a square root of 0 on one side. Negative 2 plus 3 is a 1. So we've got a square root of 1 on that side. Minus 1 still. Square root of 0 is 0. Square root of 1 is a 1. 1 subtract 1 is a 0. Yes, it did check out. There it is. X is equal to negative 2 is the answer. Okay, and the next one, hey, it's actually finally a third root instead of a second root. So do we have to check our answers? No, it'll handle the negatives and it handles the positives like that earlier here. So perfect. So let's see, since it's a cube root, what should we do to both sides? Yeah, we're going to cube both sides this time. So let's go for it, cubing the right, left and the right. Again, the radical has to be by itself though. That's the only condition. Alright, cubing something that's a cube root, that goes away. Left with 3x minus 7. And let's see what we got here. 2 times 2 times 2. 8 is good. Adding 7 on both sides gives me 15. Divide by 3 gives me x equals 5. And done. Again, as long as you're confident you did it correctly, don't need to check. But if you want to double check, you can absolutely double check just to make sure. Okay, the next practice problem here actually needs a little bit of an introduction. We'll move on to graphing. And the example problem and the practice problem actually deal with two different things. So let's actually look at the example problem from the textbook. This one's slightly different than the practice problem. So we're going to graph these guys. So first we're going to look at the difference between a square root and a cube root. What happens there? And so remember, we've been dealing with this here. A square root cannot handle negatives. So if I plug in a negative 4 into that, square root of negative 4 doesn't exist. Plug in negative 1, doesn't exist. How about a 0? Is it okay to have a square root of 0 is 0? Square root of 1, 1. Also, we've got to think about what numbers should we plug in so we get nice numbers out of it. So, yeah, I would not plug in a 3. I would not plug in a 2. I would plug in a 4. Because square root of 4 would give me that 2 that I want out of it. Again, 5, 6, 7, 8, not going to work, but 9 would work great because square root of 9 is 3. Okay, over here, though, this is a cube root. Again, we're going to think about perfect cubes this time. But can a cube root handle negatives? What's the cube root of a negative 8? This is from 6.1. Can I get that? Yeah, cube roots can handle negatives. So my question is, what do the graphs look like? And what's the difference between the graphs? That's what I want to see. So when I graph it, perfect squares, I plug in some negatives, they don't work. Plug in some positives, perfect squares, and yes, they do work, and that gives me this. The graph starts off at 0, 0. And it sort of starts curving. It goes up, it's kind of steep at first, and then it starts curving slower and slower and slower and slower forever. Okay, what does the graph of the cube root look like? Again, plugging in perfect cubes this time. So negative 27, cube root of negative 27 is negative 3, cube root of negative 8 is negative 2, cube root of negative 1 is negative 1. And again, notice the cube root function is a little bit different. It goes from negative infinity. I can plug in whatever I like into a cube function. Square root function, I can only plug in zeros and 0 and negative and positives. Okay, there's a difference between those two. And that's what the book wants to get you to think through here. So there's a difference there. Also notice, I guess we should notice how this one sort of starts and it kind of, it's almost like stretched out faster than this one here. Remember, this one sort of comes up a little higher, right? It's going up going to have a little more steep. This is a lot more shallow and sort of extending out faster that way. So kind of be mindful there too. Okay, but our practice problem deals with these two. So again, a different concept, still working with the same function, but the question now for the practice problem is this. What happens if you have a 3 that's actually outside of the square root and we're adding to the square root? Or what happens to the square root if the 3 is actually inside? Cool, so we're going to take a look at those. So let's go with the table. So for that first equation here, we're going to make a table. So again, think about what's going to produce nice answers. Square root of 0 is good, right? Square root of 0 is 0 plus 3. 3. I like that. Just a nice answer. What's another one? Plug in, that would be nice. 4 would work. 1 would work, right? Let's plug in a 1. Plug in a 1 in that. Answer is 4. 2, nope. 3, nope. 4. Square root of 4 is 2. 2 plus 3 is 5. And 5, 6, 7, 8, nope. 9. 9 would work. So square root of 9 is 3. 3 plus 3, 6. Okay, good there. There's our table. We're going to graph it all together here. So let's leave that aside for now. This one's a little bit more tricky to make a table for. So now the question, you got to think in your head here, okay, what do I plug in? When I'm going to add 3 to it, is it going to produce a nice number? And you can try some. It may not be in a nice, coherent manner. That's fine here. So I heard 6. Yeah, 6 plus 3 is 9. Square root of 9 is 3. Thinking more of lower numbers here. Yeah, negative 3 works, huh? Look at that. Negative 3 plus 3 gets you that 0. And square root of 0 is 0. So negative 3 actually produces the 0. Negative 2 would work, yeah, because negative 2 plus 3 is a 1. Square root of 1 is 1. Yeah, positive 1, huh? Because positive 1 plus 3 would make a 4. At that point, then you got yourself a 2. And then let's put in the 6 as well. 6 plus 3 is 9. That'll be the biggest number we would want because the graph doesn't even go that far anymore. Okay, so the distinction. When you get to pre-calculus, which is math 15, what we do is we spend a whole section and we just review all the functions and their graphs. So review, okay, what does a line look like? Cool. What does a parabola look like? What does a square root function look like? Right here. This one is right here. What's a cube function? How about a cube root function? We sort of have that as sort of one of the sections here. Okay, but this is part of it. Okay, so let's go 0, 3 is up there. 1, 4. 4, 5. And 9, 6, not going to graph it. That's a little too far. But here's my graph. So what did the little 3 all the way at the end do for me? Yeah, it shifted the whole entire graph up 3 units, right? Square root function got shifted up 3 units. Okay, so how about let's do the next one. So negative 3, 0. Negative 2, 1. 1, 2. And then 6, 3. Yeah, I guess the graph is part of the graph. Okay, so 6, 3. Graph, which mine has a little dip in it, so make sure yours doesn't have a dip in it there. I accidentally had a dip. All right, now question is, what did the plus 3 inside the function do? Yeah, kind of weird. You would think it's going to actually move it to the right because it's a plus. But in fact, no, it moves it to the left because, again, in order to get to 0, you got to put in a negative 3 to get to that 0. So it shifts it the opposite way. All right, with that, I think we're good to go.